Okay, hi, and welcome to Git Behind the Scenes. My name is Daphna. I'm a data scientist at Trax, formerly a backend developer, and before that, I was partly in charge of DevOps for my team, and I helped move in a previous company from Subversion to Git. And at Trax, we are using computer vision to extract insights from retail shelves, and we're also using Git to do this. It's a very important part, obviously. We're going to start with our WIFM. What's in it for me? Probably most of you are using Git. You're committing, and you're pushing, and you're pulling, and everything works fine until it doesn't. And for a lot of people, when something goes wrong with Git, we just have no idea what just happened and how to get out of this entire mess that we've brought upon ourselves. And I think that if we understand a bit more about what goes on behind the scenes and how Git actually works and what's really going on there, we'll have an easier time getting out of these Git pitfalls, or even hopefully just not getting into them in the first place, which is even better. So today we're going to be talking a bit about what Git actually is. We're going to be focusing a lot on the local repository, and we'll talk about the Git objects that make up Git, the staging area where we create commits, our use of branches, which is a really strong point for Git, and obviously combining these branches, which is what it's all about. And then at the end, we're going to be talking a bit about the remote repository, which is, of course, also important. So we'll start with the basics. We're going to be talking a bit about what is Git. So Git is a distributed version control system. This means that every developer's copy on their local machine is also a repository. So we have a remote repository. By default, it's named Origin. And we also have a local repository on each machine. Now we have to communicate explicitly between these repositories using commands such as push and pull, which we'll get to at the end. And for now, we'll talk about the local part. So many other version control systems are delta-based, like Subversion, for example. This means that they save the delta between the previous version of the files and the current version of the files. But Git is different. You can think of Git as a stream of snapshots, because what Git does is save a snapshot of our directory, of our files, every time that we make this commit. And then we have this long linked history of all of our snapshots. So again, a stream of snapshots. And Git is a mini file system. So we have a hidden directory, it's called .git, and inside are all of our files or objects that Git creates, which we'll see in a minute. And it's really a mini file system. And while we continue in this talk, I'm going to be referencing this .git folder and talking about how all the different objects sit in this directory. So again, we're going to start with the local part. And this part is relevant even if we're sitting in some dark, dank, internet-less basement, working by ourselves, or if we want to be a bit more positive, maybe we're on some nice, sunny beach, tropical island somewhere with no Wi-Fi, and we're working by ourselves. All of this first part of the talk is going to still work and still be relevant. And first up, we're going to be talking about the objects. The objects are a really important part of Git, and there are 4 basic objects that make up Git, and we're going to be starting with an example. So let's say this is a repository. Okay, we have some code files, and we have a directory, a subdirectory, and inside are some more files. Let's see how Git actually makes this work. So first of all, we have the blob. Okay, the blob will save the contents of a file, just the contents without the actual file name. And this means that if we have for some reason, several files with the same content, they could be saved as just one blob. And the blob is then compressed, so we're saving space here. And an important thing to know is that each object in Git will have a unique identifier. It's called the SHA-1. It's a hash, this hexadecimal string of characters. and it uniquely identifies this object. Now, it's not very convenient or easy to remember or use, so thankfully, we can use just the first 7 digits, which is great. And after the blobs, we have the next object, which is the tree. The tree is like a directory. What it does, it saves pointers to the blobs beneath it, or the subtrees, and it also saves the name. So now we have the name of the blob. And again, this will have the SHA-1. And afterwards is the commit, which is probably the first object that most people that work with Git will actually know. And the commit points at the top level tree of our repository. And it's really a snapshot of the way our work was at a certain moment in time. So it will contain blobs of the files that have changed in this current commit and the trees. And it has an author, and it has a timestamp. It's pointing at the tree, and it also has a message, because the commit is supposed to be able to tell us why we were making these changes and what we were going to achieve with a certain commit. And after that, our fourth object is the tag. There are 2 types of tags in Git. It doesn't really matter, but the important thing is that a tag enables us to name a commit. Usually this will be, for example, this is version 2.0 and this is version 2.1, and it's pointing at a specific commit. Okay, so now we understand what a commit is, but how do we create it? And for this, we have the staging area. Now, this is, again, something that's special in Git. In Subversion, for example, every file that you change is going to go into your next commit. And that's not always what you really want. Sometimes we're going to be working on many different files. And in Git, we want our commits to be small. We want them to tell a story. And this way, it's easier to revert. If we decide to go back on some work we've been doing, we can more easily go back without deleting everything. It might be easier to review. It's also easier if you want to cherry pick some changes to a different location. And sometimes we changed many different things, and we don't want to commit them all together. So in Git, our working directory is decoupled from our repository. And the way this is done is like this. So we have our local repository, that's the .git directory. And we have our working directory, that's just the files, our project that we're working on. And in between, we have this staging area, or the index, and that's where we write changes that we're going to put in the next commit. So we have to do this explicitly. What we're going to do is git add the files that we want to add. Add has actually it works in 2 ways. First of all, if there's a file that Git isn't tracking yet, git add will make Git track this file. And the next time, git add will add these changes that have been done since the previous version. It will add them to the staging area. Now we can also add just parts of files using git patch. That's more advanced, but sometimes we might want to add only parts of the file that we've been changing. Now, after we add, the changes are written to the index. And now, when we commit, we do git commit with some message. Git will take these changes. It will create the appropriate blobs and the trees, and finally the commit message. And it will store them in an objects folder in our .git directory. Now, what we need to notice here is that if we made changes to a file and we staged it, and then we continued working on the file, then when we commit, only the changes that have been staged will go into the commit. So that can be a really useful tool. Many times we want to stage and commit all of our changes. So for that, we can commit with the -a flag, and then it'll just take all of the changes in the working directory and put them in the next commit. So, okay, now we understand how a commit is created. And the next thing to understand is branches, because branches are these links of commits. So first of all, let's understand why we need branches. And again, a branch is a really strong part of Git. In Subversion, when you want to create a branch, you are copying all of your files. And that can take a long time, even minutes. So it's really not something that you're going to be doing a lot in your day-to-day work and going back and forth. It's really not easy. But in Git, creating files and creating branches and changing to different branches is very fast and very cheap and very efficient. And the reason we want to do this is usually we'll have a main branch, and by default it's called master, of course. And on this branch, we want to have our very stable, thoroughly tested code. But obviously then we want to develop new features and we want to try something new. Maybe it'll work out, maybe it won't. We want to try this, and many different people may also be working on many features at the same time. And at the end, we'll want to bring them back into our main branch. So being able to quickly create, modify, and delete branches is very important to our work. And what happens is that commits are organized in a directed acyclic graph. Apart from all these previous parts of the commit, as we said, the message and the author and pointer at the tree, we also have pointers to our parents. A commit can have 0 parents if it's the first initial commit in a repository. Most of the commits will have 1 parent, and they can also have 2 or more parents, which we'll see later on. So the next thing we have to create our branches is the references. And references, along with objects, are another very important part of Git. Our references are just pointers. They're actually a small file. If we have our .git directory, then inside we'll have reference folder, and inside it we'll have branches. And they're just a small file. The name will be the name of the branch, in this case, master, for example. And the content of the file will be the SHA-1 of the commit that it's pointing at. This commit is the tip of the branch. So now we understand that creating a new branch is just creating this small file, and modifying a branch is just changing the SHA-1 inside it, and deleting a branch means deleting a small file. And that enables this very quick work with branches. And we have another special kind of reference, which is named head. Head will point at the branch that is currently checked out. And this is really the files that we're going to be looking at this moment will come from this commit that the branch is pointing at. So the best way to understand this is by looking at an example. So let's go ahead and see this example for branches. Let's say we have this initial commit, and then we have another commit. You can see that the master reference is pointing at this commit, so that's the tip of the master branch. And head is pointing at master. Now let's say we have some really cool new feature that we want to work on. So we're going to create a feature branch. We can do this with git checkout -b my feature, which actually does 2 things. It will create the branch and check it out. If we want to only create the branch, we could do git branch with the name of the branch and then git checkout. But usually, if we're creating a feature branch, we might also want to check it out, so we can use this. And now we have a new reference, my feature, and it's pointing at the same commit. And head is pointing at this new reference. Okay, so now we change stuff and we make a commit, and we maybe make another commit, and then we want to move back to master. So now if we check out master, my feature stays where it was, and master stays where it was, but head has moved to master. Okay, so we said that head points at the tip of a branch, but head can also point at a specific commit. Why would we want to do this? Maybe our tests are currently failing and we want to check if previously they had worked or not, or we want to go to a certain point and branch out from there. It could happen. So in this case, we can go to the log and look at the SHA-1 of this specific commit, and then we can check it out. And now we're in a state that Git calls detached head. This means that we're not pointing at any branch, but at a commit, somewhere in the middle of nowhere. And what happens here is that we can look around, and Git will tell us so. We can try whatever we want. But if we want to make changes and save them, we can make a commit now. But if we move away from that commit, what happens is that no one is pointing at it anymore. And at some point, the garbage collection will come along and look for all kinds of objects that no one is pointing at, and it'll take them away. So if we make any new work while we're in detached head, we have to create a new branch or some tag, which is really a static reference, to point at it. If someone is pointing at it, it's fine, it won't be lost. Now that we've created branches, we at some point will want to merge them back to bring all of our nice new work into master. So there are two ways in Git to combine our branches. We have merge and we have rebase. And with merge, again, there are two ways. We have the fast forward and we have the merge commit. So back to our example, where we had master and we had my feature, and now we want to merge it back in. So in this case, we can see that it's really a long line of commits, and there's really nothing differentiating where master is from my feature. So if we want to bring our my feature work into master, really all we need to do is move that master pointer along to the end to point at my feature. And that's exactly what will happen when we git merge. So master will just move along to my feature, and we're done. And we can all go home now and be happy. And we can, if we look at our history, we'll have this nice linear history, and there's really no way of knowing there was even a branch here at all. Okay, but sadly, life is usually not that simple, and it's not the regular case. So let's see what happens if it's not that simple. If we go back to our example, let's say that we were working on my feature, and if we're by ourselves, then maybe we had to go back to master for some hotfix because we found a bug. And what's usually the case, when we are working with other people, maybe someone else has already put their work on master. And now we have some new commit on master, and maybe even after that, we have a commit on our branch. Now, we want to combine the branches, and there's really no obvious way where we can just move our pointers and have done with it. It just won't work. We'll lose either one or the other of the branches. So what we do now when we commit is we create a completely new object. If you notice that earlier for the fast forward, we didn't create any new Git object. We were just moving references. But now we have to create a new object, and this is known as the merge commit. And this is the commit that can have two parents. It's pointing at both of the branches. Now, something to notice here is that usually when you work, you have your master branch, you have your feature branch. Usually you will be bringing your master branch into your feature branch and making all of your tests there, because maybe there's something that doesn't work in the new additions to master with your work. And only when you see that everything works, you will be pushing it back to master. But now, just for simplicity's sake, for our example, let's say that we're always merging our feature branch straight to master. Just keep it in mind. Okay, so we merged our feature into master. We have this new merge commit. And something to notice here that didn't happen in the fast forward is that there could be conflicts. Git is very good about merging in general. If you have changes to different files, if you have changes to different parts of the same file, it's all good. But if both of the branches have changes to the same part of the same file, obviously Git has no way of knowing which one is the preferred one and what you want to go with. So at this point, Git will stop. It will tell you you have a conflict. You will need to solve it manually. And once you're done, then you tell Git to go on. It will create the merge commit. And this merge commit will also include the information about how the conflict was solved. So, okay, sometimes you're working on your merge and you changed files you didn't mean to change, or you realize that you really shouldn't have merged this branch into the other branch, and you can only describe the situation as something like this, and you're starting to doubt your life choices at this point. So that's fine. We have git merge -- abort, and there's a way out, and Git will help you. You can go back and rethink your steps, and again, maybe these were the wrong branches, or just do it over, and I'm confident you can do it this time. So we talked about the merge, that's the fast forward, and the merge commit, and now we have rebase, which is really something different. Rebase is really rewriting history. What happened in the merge commit is that we said, okay, this is the history, and now let's combine it. In rebase, what we're saying is, let's change the history. So if we had this example with our changes to master and to my feature, what we can say is that conceptually, it doesn't really matter who made what changes before. It doesn't matter if our fourth commit happened before the third commit. What we really want to do is take all of our feature and put it just at the end of master. This is really what we do with Rebase. So if we rebase master onto our feature, we're going to take all of the commits from our feature branch and put them at the end of master. But the thing to notice here is that Git commits are immutable. We can't really change what they have inside them, and because they have the pointer to the parent, then we can't just move them here. What we're going to do is we're going to travel to the end of master, and then we're going to replay the content of each commit on top of the previous commit and create a new commit that can look the same. It might have the exact same content, but it's not really the same commit. If we look at the Git log, then we'll look at the SHA-1 and see that it's really a completely new commit. Okay, so while we are making this rebase, we're going to be visited by our friend, the detached head, because Git is really pointing at each one of the commits during the rebase, and so it's in a detached head state. And you might at some point have a rebase that goes wrong, and you could find yourself stuck in this detached head state. So the thing to remember is, again, there is a way out, and you can just rebase abort like you did with the merge, and you'll be fine. But if we go back to our rebase, and we said that we have completely new commits here, so the thing to know here is that we can have more conflicts than we did in the merge. With the merge, you could have conflicts in many different files, but you only encountered them once when you were merging. And with the rebase, you could have as many conflicts as the amount of commits that you are rebasing, because for each one, it'll go and it'll replay it, and it could change the same line in the same file, and then we're doing it again and again. So this is something you'll have to solve each time. And then when we're done, what we do is we can merge my feature, and you can see we have the situation that we had with the fast forward merge. Now we have this nice linear history, and we can just move our pointer forward from master to point at the feature branch, and then we're done. We have this, we've made this rebranch, we changed our history, it's now nice and linear, and there are no additional Git objects like we had with the merge commit. But we have to remember something here, that all of the commits that we rebased are completely new. So this brings us to a really important rule in Git, and that is you should never rewrite commits that you have shared with others. Or to be more specific, you can't rewrite commits that you've shared with others and that others have based their work on. And I add this because I do sometimes push, we haven't talked about push yet, but I do sometimes push rebases onto a feature branch that I work on, because you can never know when your personal computer is going to go up in flames. It could happen. And then you don't want to lose your work. So sometimes you do put your commits on a remote branch, and then you might rebase and you want to put them there again. But I only do this because I know that I'm the only one working on this feature branch and no one else is. If other people are working in a branch, you under no circumstances should do a rebase on it, and that's because you are changing the history. And as we said, Git is this long link of commits pointing at each other. When you break the history, you can no longer merge, you can no longer do any of this work, and your coworkers will not like you in any way if you do that. So don't. Okay, now that we talked about the two options of combining branches, which one of them is preferable? There's no straight answer for this. There are pros and cons in both ways. With merge, you could say that you have an accurate description of the history and of what really happened in your project. Because you also have these merge commits, if you look at the history and you see all these branching out and going back in, and you can see which commits were parts of which feature. And sometimes that's a good thing, but it can also be really, really messy. And with Rebase, you have a nice linear history that you can tell the story of your development really well, even if it's not exactly what happened while you were developing. And maybe even if you want to revert certain changes, it could be easier because the commits aren't all jumbled up. So really the important thing here is that each team or each organization decide what the best strategy is for them and then just stick with it. Now, if we want to talk about remotes. So up until now, all of this happened on our local machine, and it could happen even if we're working by ourselves. But sadly, we can't work by ourselves all the time. It's this part of our job where we have to work with other people. And so we do want to understand how Git works with a remote repository. But the thing to understand here that almost everything in Git happens locally. Even if you are doing things on the remote repository, you can't do them directly. You have to bring all the info into your local repository, make the changes, solve your conflicts. All of this has to happen locally. And only then you can push it to the remote repository and share it with everyone else. So again, we'll do this with an example. And here we have our commit object. And we have two references that we already know and love. We have master and we have head. But here we also have something new, and this is called a remote reference. And again, if we think about our .git directory, then we have a folder for remote references. And again, these are just files, but they're showing us where the remote branch was pointing. Again, last time we talked with it. Because as we said, we have to update the remote repository, but it doesn't happen automatically. And we have to explicitly ask the remote repository what's new and tell it what's new with us. So here, origin master is still pointing at this initial commit. And then later on, we have a local commit that we made. And now we want to understand what's happening at the remote repository. Okay, so we'll use git fetch. Maybe some of you aren't familiar with git fetch, and that's fine because soon we'll see a command that everyone is familiar with. But what git fetch does is it brings in all the information about the new commits that we have in the remote repository. In this case, we have 3 new commits on our master branch. And it also updates the references to point at where they should be pointing. So now origin master is pointing at the tip of these remote commits. And if we remember the examples we had earlier, we can see that this is a situation for our merge commit because we have local changes and we have remote changes, and we can't just move our pointers and solve everything. So now what we're going to do is git merge. We're actually merging with origin, our remote repository, which is by default named origin. We could also name it anything else. And then again, we have this new merge commit created. And after we create that, now we can move our remote reference pointer to just point there. And the thing to remember is that there's this command git pull, which is what most of you are probably familiar with. And git pull does these two things. It does the fetch and it does the merge together. Some people do prefer to do it separately, to fetch and then know that they can look at all the changes and only merge once they're sure that what they're bringing in is important. But most of us just git pull and bring in all the remote changes as they are. So once we do this, we can git push. And with push, we are actually moving our remote reference and letting the remote repository know that we've moved this reference. And now we have we are updated with our remote repository. Okay, so that's great. But sometimes, what happens if we didn't want to do this merge before we pushed? You know, maybe we didn't know that there are changes in the remote repository. Maybe we made our changes and now we just want to push. Okay, so Git will tell us, no, you can't push. There are changes in the remote repository. But what if you really, really want to push? And we could, in that case, use force push. But what would happen? And we actually had that happen in Trax several years ago, where someone had an outdated version of the repository, and they made some changes, and they wanted to push, and they really, really wanted to push. And then what happens is that you overwrite your repository history with the local history that you have. And that's really not nice at all, because then you could lose, in that case, about like 2 months worth of commits, and your coworkers will now definitely not like you. Thankfully, if we remember that we have a distributed version control system, and because every developer's copy of the repository is the complete repository, we can just take the history from someone else and save the day. But if you reach a situation where you have to use git force push, just be really, really sure that this is what you want to do. It could happen, but be really sure. And again, if we go back to our example and we have this remote and we have this merge commit here, then maybe when we were merging two branches, there was a use for this merge commit. But now when we're doing it locally and we're just merging between master and remote master, then you could say it's just littering our history and our log. You could also pull with the -- rebase flag, and that will really rebase your local work on top of the remote master tip. And that will make it a bit cleaner and nicer. So, okay, to recap, the important things to remember are that most of the work in Git happens locally. We have these objects and we have these references. It's really what Git is all about. And all of this work is done locally on our repository, and then we just update the remote and ask what's new with you. Now remember the first rule of Git. Please only rebase, only change the history on something local and not on something you've shared with others. And hopefully, now that we understand a bit about how Git actually works and what's going on behind the scenes, we'll be able to get out of these pitfalls or avoid them altogether. So thank you.